Hello everyone, my name is Yibin and I come from Hong Kong UST. And today I will present my work, Law Towards Consistent Low Latency in 802.11 Home Networks. So as a key use in nowadays internet, ultra-low latency application impose strict latency requirements and a tail latency problem in network services. For latency requirements, ultra-low latency application require a deadline of 100 milliseconds. However, in contrast, in real-world network service, although we can provide average latency at around 24 milliseconds, the tail latency at 99 percentile, 99.9 percentile is still higher than 200 milliseconds. And also a lot of previous work have already proved that. So there are still huge gaps in how to provide stable and consistent low latency in home Wi-Fi networks. And our observation is that Wi-Fi lasthop is the bottleneck. And as an interesting data, the base RTT is already very low nowadays, thanks to CDN and edge servers. And users can normally reach to these nearby CDN and edge servers within 10 milliseconds, which means the network backbone has been highly optimized, as shown in this figure. So in the previous decades, the Wi-Fi lasthop may be, the latency in Wi-Fi lasthop may be much shorter than the overall RTT. But nowadays, the latency in Wi-Fi lasthop is becoming more and more comparable to the overall RTT. And also, we conduct experiments to see exactly how much the Wi-Fi lasthop contribute to the tail latency, as we can tell from the figure. When the end-to-end latency is higher than 70 milliseconds, the Wi-Fi contributes to up to more than 95% of tail latency for most of these situations. And the key reason behind is existing Wi-Fi is not designed for ultra-low latency applications. It's designed for optimizing some other metrics, such as fairness, goodput. So we further break down it into three parts. The first reason is there are too many queues in the Wi-Fi link layer. As in the figure, we have flow queues, retry queues, and hardware queues. Each layer has independent queues as their own scheduler. So they work independently, and they even don't know the existence of each other. And each queue adds unpredictable delay to the packets. So actually, this kind of queuing management is designed for throughput and fairness, not for stable low latency. And the second reason is current retry management is not insensitive to delay. Besides these three layers of queues, we also have two layers of retransmission in current Wi-Fi link layer. First is the hardware retransmission. After a packet enters the hardware in Wi-Fi link layer, it will do a row of hardware retransmission. And between two hardware retransmission, there's a management interval, which consists of SIFS, act timeout, DFS, and back-off condition window. And the management interval can take up to several millisecond delay. And so in these several times of hardware retransmissions, it can take dozens of milliseconds latency in total. And the second layer is the software retransmission. It's actually some additional retry round in the Wi-Fi driver, because Wi-Fi packets will only be dropped after dozens of hardware retransmission. So after the packet failed for some times in the hardware queue, it will be pushed back to the driver. But if the driver still thinks that this packet can be transmitted, it will push back, return the packet back to the hardware queue. So this whole process will lead to more than 100 milliseconds delay in total in some extreme situation. So this kind of retry management is delay insensitive, and it's trying to ensure reliability rather than low latency. And the third reason is the rate adaptation in current Wi-Fi link layer is agnostic to the queuing delay. So the rate adaptation in Wi-Fi now is goodput oriented and physical channel based, which means the rate adaptation will monitor the physical channel quality and then choose a data rate based on the physical channel quality, which can balance throughput and packet loss rate in order to get a highest goodput. And here we present a real-world trace. And it consists of 60 packets. And the index means the MCS index. The higher the index, the higher the data rate. So first, at the packet 11, the packet is lost here, which means the channel starts to fluctuate. And after this packet, in the pink area, the packets inside this area conducted massive retries, which will result in the increase of queuing delay. And at around the packet 21, the rate adaptation downgrades the data rate, which means the rate adaptation wants to send slowly when the channel starts to fluctuate. But it will further lead to the increase in the queuing delay because we stand slow, but the queue is still building up. And also, we can easily tell that the queuing delay increased rapidly, but it decreased slowly. That's because the multi-layered queue cannot handle this sudden latency spike. However, we have our opportunity here. Ultra-low latency applications are loss tolerant to some extent. Techniques such as forward error correction, FEC, which is adding some redundancy to the packets and can recover the lost packets. Also, some error concealment algorithm by applications, such as video codecs. And the third is latency-sensitive congestion control, such as BBR, COPA, GCC. They care more about the latency, not about the packet loss rate. So here we conduct an experiment. We add 1% additional loss, but the tail latency doesn't increase a lot, thanks to the FEC. So our key insight is we should consider dropping packets instead of queuing them for too long, as shown in this green figure. What if we simply drop this green point, the packet at the green point, and adopt a different policy for rate adaptation? So we can easily eliminate the latency spike here. So we propose our work, LAtency-bounded Wi-Fi link layer. And the basic idea is super straightforward. We just actively drop packets that is expected to suffer latency higher than the latency bound we set in advance. So let's look back to the 3 gaps in Wi-Fi link layer. In order to address these 3 gaps, we propose our two-step design. First is the queuing structure reshaping. And the second is fine-grained latency-sensitive rate and the retransmission joint control. Let's talk about the first design, the queuing structure reshaping. And the key changes here is that we simplify multi-layered queues. First, we move flow queue down to the driver. And second, we eliminate the retry queues in the driver. At last, we keep at most 2 packets in the hardware. By doing so, we can have a maximized transmission opportunities for unified queuing structure. So we want to keep 1 packet standing at the hardware and 1 packet waiting at the hardware. Because if the standing packets finish the transmission, but we do not have 1 extra packet waiting in the hardware, and we now get a new transmission opportunity, we will lose this transmission opportunity. And it will lead to the overall performance degradation. And what can we do based on the unified queuing structure. For example, we want to have a 30 milliseconds overall latency bound. In our multi-layered queuing structure, we may set 10 milliseconds each to the different queuing layer. So first, if our packet have 12 milliseconds latency in flow queue, we will drop it. But the overall latency of this packet is far from the latency bound, 30 milliseconds. And it's the same for the driver queue. If our packet have 12 milliseconds delay in the driver queue, we will also drop these packets. But the overall latency is still lower than the 30 millisecond latency bound. Also the same for the hardware queue. So that's all unnecessary packet loss. So with this unified queuing structure, you could have a centralized latency management and active packet dropping. So the benefit here is centralized control minimizes unnecessary packet losses versus per layer limits. And the second design is rate and retransmission control. And the key changes in this design is first, we adopt fine-grained control. Because current rate adaptation, the rate is updated every few packets, but we do the update per transmission opportunity, which means we even update the the data rate of the packet when they are in the hardware. And it allows rapid reaction to the channel quality. And the second change is we add a cleanup state. So in cleanup state, we adopt more aggressive rate and retransmission limit settings, which means we simply send faster and do less retransmission in this state. And we can eliminate latency when queues start to build easily by doing so. However, it will lead to consecutive packet loss. So we finally add a loss pattern control. Because the upper layers recovery capability cannot handle too much consecutive packet losses. So we want to avoid this kind of consecutive packet losses and keep loss within upper layers recovery capabilities. So by doing so, we can maximize goodput on the bounded latency while keeping loss within upper layers capabilities. And here is our experiment result. We did our experiment from two perspectives. First is on the packet level. So we implement a law on OpenWiFi, on SDR pipe, and choose three baselines, Minstrel, LLIA, and Thompson sampling. We use Apple for UDP sender on the edge server, and the sending rate is 10 megabits per second, and each test will be run for more than 10 minutes. So law could achieve up to 83% per packet latency improvement at a 99 percentile, with almost optimal packet dropping, which means we can keep the packet loss rate lower than 1%. And also, we can see clearly as the purple line, there's a cutoff here, which means the latency bound is in effect. And all these three other baselines have a very long tail. And the second part of experiments is application level. We choose WebRTC as a typical ultra-low latency applications. And the application setting is 10 megabits per second and 30 frames per second. The sender is deployed on our edge server. Law could reduce 99% of frame delivery latency by more than 58% compared to baselines. So law also performed very well in application level. So the key takeaways of this work is first, Wi-Fi lasthop is dominating the high tail latency of ultra-low latency application. The second is existing Wi-Fi is not designed for ultra-low latency applications. Third, upper layer loss tolerance enables a new design choice. We could drop earlier rather than queuing them for too long. And the last one is law provides consistent low latency with bounded delay, control the loss, and high output. And that's all.